Whereas to find the maximum and minimum points and values of f of x, which is given by 1 over the quantity 1 plus x squared on the interval, closed interval, negative 2 to 2. So let's just take a look at the graph of this first so that we can see what we're trying to work with. Okay, so let me go ahead and draw that out. I'm going to go down here like this. Okay, now at the endpoints, so here's 2, here's negative 2. When x is 2, so f at 2, that's 1 over 1 plus 4, which is 1/5. So we'll say this is a height of 1/5. Now clearly when we plug in negative 2, we get 1 over 1 plus 4, the same value, which is also 1/5. And if you take a look at this function right here, this is an even function. So we have symmetry along this line. Okay. Now if I pick values like, let's say f at 1, okay, f at 1 is 1 over 1 plus 1, which is equal to 1/2, which is also equal to f at negative 1. And again, definition of the even function. So let's go up here to a height. So we said this was 1/5. Let's say this is 1/2. Here's negative 1. Here's positive 1. So we're up here. Okay. And if we look at f at 0, okay, we get 1 over 1, which is 1. So that point is up there, just like that. Now the function, and we'll talk about this in a minute, does change concavity, okay, from concave up to concave down back to concave up, and it looks something like this. And we can discuss why it looks like this using our derivatives and second derivatives, okay? But this is the general picture. It kind of got this like this little bell look to it. So it's clear from the picture that f of negative 2, which is at f of 2, is the minimum value, which is 1/5. So we have a minimum value here, and it displays here as well. The minimum value is the same, but at two different function values. Okay. We also know that we have a maximum value here at f of 0. So the maximum value is 1. Okay. Now how can we prove that? Because just using a function like this, well, that's not a proof. So what we're going to do is I'm going to show you, we're going to demonstrate that f of 0 is a max. Okay. Well, there's a couple ways to look at this. The first is to take the derivative. And so we know that f prime of x, so we have to take the derivative of this guy. So it's low times the derivative of the numerator, which is 0, minus the numerator times the derivative of the denominator, which is 2x, over the denominator squared. So that gives you negative 2x over 1 plus x squared squared. The only time this guy is equal to 0, the only x value that gives this equal to 0 is when x is 0, because the bottom never can be 0, so the only way to make a fraction 0 is to make the numerator 0. So here's your x equals 0 value. So 0, 0 is a critical point. Okay, now let's look at f double prime at 0. So the derivative of this again is the low times the derivative of the top, so negative 2 times 1 plus x squared squared. So low times the derivative of the top minus the top times the derivative of the bottom. Now the derivative of the bottom's a little ugly. Okay, so this is going to be, that's a multiplication symbol, by the way. Okay, so it's going to be 2, 1 plus x squared to the first power times derivative of the inside over the denominator squared. Okay, let's clean this up a little bit here. So I'm going to factor out a 1 plus, actually I'm going to factor out a bunch of stuff here. I'm going to factor out, let's see here, I've got 2 times 2 times 2, and I got a 2 here, so I'll factor out just 1, 2, and I'll factor out a 1 plus x squared, and then I'll be left with, in fact, let's drop out a negative 2, okay, and then I'll be left with, I can drop this as well. Well, actually I can't. 1 plus x squared. Well, I can. Okay, so this was minus, so now it was plus, but it's going to be minus since I pulled the negative out. And then I pulled a2 out, so I'll have 4 x times x, so 4x squared. Okay, so that's this 4x squared times, now 1 plus x already got pulled out, so I don't have to multiply it in there. Over 1 plus x squared. Now what we want to do is verify that the second derivative is not 0. Because if the second derivative is 0, then we don't have a change in sign on the first derivative, which means we don't have a min or a max. Okay. So here when the second derivative at 0, I got to plug in 0 here, so this is going to be equal to negative 2 times 1 times 1 plus 0, so that's going to be, and that's over 1. So this is clearly not 0. So we've found a min or a max, okay, and so we know that this is a maximum. There's another way of looking at this, which I think is important. What we could do is to show that this guy, where is it, that 1 is a max, is we just need to show first that f of x is less than or equal to 1 for every x which is in I, and I is the closed interval negative 2 to 2. So let's go ahead and take a look at, so this was the first way. Let's go ahead and take a look at the second way here. We want to show that this is true. Well, f of x is given by 1 over 1 plus x squared. We want to show that that's less than or equal to 1 for all x values. Okay, so how are we going to do that? Well, we can go through a couple arguments. Okay, the first we can do is we can say that so I'm going to go through the argument here and say, okay, x squared is clearly greater than or equal to 0 on this interval. That implies that x squared, actually even moreover than that, no, let's leave this like this. That implies that x squared plus 1 is got to be greater than or equal to 1 on this interval. Okay, so we're gonna prove this. We're gonna prove that this guy right here is true. So our first step is to say, well, x squared is greater than or equal to 0. That implies that x squared plus 1 is greater than or equal to 1. That implies that the reciprocals 1 over x squared plus 1 is less than or equal to 1 over 1, which implies that 1 over x squared plus 1 is less than or equal to 1 for all x on the interval I. And we've just now shown that this is true. It wasn't that hard to do. And in fact, what's slick about this right here is, one, I didn't use any calculus, okay? And two, the argument is super easy to follow, okay? Both these are valid ways of showing a maximum. Now let's take a look at the minimum. Now the problem with the minimum is that these guys are not critical points, so I can't use my derivative test. So what I need to do is I need to show, to prove the minimum is 1/5, we need to show that f of x is, let's see here, greater than or equal to 1/5 for all x in the interval. Now we also should show, and I didn't say this up above, we also know f at 0 is equal to 1. So this in combination with this right here, well, that clears our first and second pieces, our two pieces for proving something's a maximum. So if we want to show, let me write this out nice and formally. So if we want to show that 1/5 is the min of f of x, which equals 1 over x squared plus 1 on the interval -2 to 2, then we're going to show the following. The first thing we're going to show is that f of x is greater than or equal to 1/5 for every x in I. So here's the proof for this. Okay, so we need to show, in other words, show that 1 over 1 plus x squared is greater than or equal to 1/5 for all x on the interval -2 to 2. Well, let's take a look at this. It is very clear that on the interval x, on this interval, okay, on the interval, let me go like this. It's clear that the function x squared is always, this guy right here is always less than or equal to the number 4 for every x value from -2 to 2. So this is clear. Okay. Then this implies that x squared plus 1 is less than or equal to 5 for every x. But this implies that 1 over x squared plus 1 is greater than or equal to 1/5 for every x. And this implies that f of x is greater than or equal to 1/5. So that's the first part. The second part is we need to show that f of some x naught is equal to 1/5 for some x naught on the interval. Well, that's easy. I can just do one. I don't have to do both. I'll just do one. F of 2 is equal to 1 over 1 plus 2 squared, which is equal to 1/5. And so now we've got the second piece there as well. So we've now proven that we have a minimum and a maximum at those values.